Hi everyone, welcome back to my videos. I like to do a tutorial on a geometry problem that was given on a high school level math competition for juniors and seniors, I believe. So this was one of the harder problems on the competition, so let's take a look at it. We're given 3 circles, each of radius 2, and each of the 2 circles intersect at the center point of a third circle. So in other words, if you have circle with center A and circle with center B, they both intersect at this point C, which is the center of the third circle. So how I set up this problem is I constructed a x and y axis such that points B and C are on the x-axis and equidistant from the origin. So O is the origin right here. So we know that the length of segment BC is going to be equal to 2 because that's the radius of the circle of center C. And therefore, by symmetry, point B is going to be 1 unit away from the origin and C is going to be 1 unit away from the origin. So B is going to be at the point -1, 0, and C is going to be at the point 1, 0. A and D are on the y-axis and are also equidistant from the origin. We can write down the equation for a circle with center C as x minus 1 squared plus y squared equals, well, technically it's 2 squared, which is equal to 4. The circle with center B has the equation, well, it's going to be x minus minus 1, but that turns into a plus. So x plus 1 squared plus y squared equals 2 squared, which is equal to 4. If I set these two equations equal to each other and I simplify, I get x is equal to 0. So if I plug x equals 0 into this equation, I get 1 squared plus y squared is equal to 4. So y squared is equal to 4 minus 1, which is equal to 3. So y is equal to plus or minus the root of 3. So a is at point 0 root 3 and b is at point 0 minus root 3. So now I'm going to construct segment AC. So we know point A has y coordinate root 3. So the distance of the segment A0, so from point A to the origin, is going to be root 3. The length of segment AC, well, segment AC is actually a radius of a circle center C. So we know that that radius is 2. So we can use trigonometric properties. The sine of angle ACO is equal to square root of 3 divided by 2. So the angle ACO is going to be equal to 60 degrees. So if we look at the area of this pie-shaped region, so ACB and then this portion of the circle, if we look at this entire, looks like a pie-shaped area, we're going to find that it's 60 divided by 360 times 2 pi times 2. We simplify and we get 2 pi over 3. So now let's draw a segment AB. So that's this dotted line in green here. The area of triangle ABC is equal to 1/2 times the base, length of the base, which is BC, times the length of the height, which is AO. So we get 1/2 times 2 times root 3. Remember, length of BC is going to be 2 because it's a radius of the circle, just like AC is. And we simplify this and we get the area of the triangle ABC is root 3. So if we look at this kind of shaded blue region here, that's kind of created by an arc of the circle and then this segment, we see that the area of the blue region is going to be 2 pi over 3, which is the area of the entire pie-shaped region, minus root 3, which is the area of this triangle. So that's just the additive and subtractive properties of areas. So if we look, there's actually 3 of these types of regions, these little kind of like things that are shaded in blue within the entire white region. So the white region is this thing here, A, B, C. So the area of the white region defined by points A, B, C is going to be 3 times this value of the blue region, because there's 3 of those regions, plus root 3, which is the area of triangle ABC. And if we simplify that, we get 2 pi minus 2 times root 3. Okay, so now the area bounded by the 2 circles with center A and center B is going to be the sum of the area of the rhombus ABC and 4 blue shaded regions. Okay, so now we're looking at this whole thing here. So we can think of the area of this whole region as a rhombus, right? And then we have to add these 4 kind of like blue shaded regions we found. So we can find the area of that as, well, we know the area of a rhombus is going to be 1/2 times the length of one diagonal times the length of the second diagonal. So one diagonal is going to be this length of AD. We know that point A is at root 3 for the y-coordinate, so this is going to be 2 times root 3 for the length, and the length of segment BC is going to be 2. So if we plug that in, we get 1/2 times 2 times 2 root 3 plus 4 times the area of the blue shaded region. So we do this 4 different times, and we get 8 pi over 3 minus 2 pi minus 2 times root 3. So the area of one brown region, so this region here, BCD, all we have to do is we do the area bounded by the 2 circles minus the area of the white region. So we're going to do this entire area here minus the area bounded by this white region. And so we can say the area of one brown region is equal to 8 pi over 3 minus 2 times root 3 minus 2 pi. Well, it's going to be minus 2 root 3. That turns into a positive. So plus 2 times root 3. These cancel. So then we're left with the area of one brown region is going to be 8 pi over 3 minus 2 pi. So we need 3 of these regions. By symmetry, we get 3 times 8 pi divided by 3 minus 2 pi. If we simplify this, we get 8 pi minus 6 pi is equal to 2 pi. So the area of these 3 brown regions here is going to be equal to 2 pi. So this was definitely a problem that required a lot of creative thought, but it was fun to solve, and I hope you enjoyed watching it, and I hope to see you in my next videos. All right, everyone, have a good night.